We mentioned earlier that given any group G, we can construct another group out of it by taking its symmetries. In other words, taking bijections between the group and itself that preserve the structure on a group. What's a name for this that we've come up with so far? Exactly. Well, so last time we saw the term automorphism, but today we use the term isomorphism. So an isomorphism between a group and itself is called an automorphism. So here's another example, or here's another sort of construction. So given G, we can construct the set denoted AutG. So these are called automorphisms, which is just a shorthand for isomorphisms between the group and itself. So this is the set, well, as I said, of isomorphisms from G to G, but in the sort of impressionistic language we were using earlier, this is the symmetries of G, or the structure-preserving maps of G. Structure-preserving. There's something that we haven't verified that we really ought to verify. So I called this a group. This is a little problematic. I mean, we know certainly that composites of isomorphisms are isomorphisms because certainly the composite will still be a bijection. And if you have, say, F and G isomorphisms, then f of G, fg xy is f of G of x, G of y, which is fg x, fg y. And the identity is certainly there. We have just the usual identity map from G to itself, and that's certainly an isomorphism. But we're missing something, and that is that inverses are still automorphisms. And that's easy to verify, but it's something you certainly need to verify. And to prove that this thing is a group, so the thing you need to verify, the last remaining thing to verify, show that the inverse of an automorphism is an automorphism. Or more generally, that the inverse of an isomorphism is an isomorphism. This isn't hard to see, but it's worth verifying to make sure that you're comfortable with the language. Homework assignments, accumulated homework assignments back on Wednesdays.